Okay, so if H2SO4, I'm going to take 2 hydrogens. They each have a mass of 1 sulfur, which is 32, and 4 oxygens, which each have a mass of 16. Okay, do you feel like by now you're getting to the point where you've got a lot of these atomic masses memorized? Yeah. Good. Yeah, that's right. I had it at 98 grams per mole. Would you agree with that? What's the name of that molecule? Sulfuric acid. Good. Don't doubt. Just say it. Sulfuric acid. You guys knew what it was. Sulfuric acid. Because if we take away the H2, we're left with sulfate. And 8 leads us to an ic acid. So we had sulfuric acid. All right. Very good. All right. What about this? The molar mass of our molecule down here. Give me the name of this one first. Ammonium phosphate. Ammonium phosphate. Okay. But here, how many nitrogens do I have? I have 3 of them. That 3 applies through there. So I have 3 nitrogens, which each weigh 14. How many hydrogens do I have? 12. Okay. And they each weigh 1. 1 phosphorus, which is 31, and 4 oxygens, which weigh 16. Okay, so 14 times 3 plus 12 plus 31 plus 64 gives me a molar mass of 149 grams per mole. That's what I had for that. Is that what you guys had as well? Okay, 149 grams per mole. We feel good about the rules for molar mass? Very simple, right? The only thing that we need to make sure that we're really careful of is right there. That 3 and the 4, they're going to get multiplied because that 3 is getting distributed throughout those parentheses. So that should feel like a pretty simple review for you, so I hope it is, okay? All right, percent composition. Once we know the molar mass or how to find molar mass of a substance, we can also calculate the percent composition, or sometimes it's called the mass percent of a different element within a compound, okay? What it allows us to do is basically compare the mass of a single element to the mass of the whole compound. So this compound is 20% carbon and 38% oxygen and whatever it is. That gives us a ratio to look at as we look through our whole thing, okay? So if I want to find the percent composition of this compound right here, I'm going to first find the molar mass. The first step I've got to do is find the molar mass. So carbon is 12, and there's 2 of them. How many hydrogens do I have? 6. Yeah, there's 1 hanging out over there. Okay, so we're going to find the mass of the whole thing. 24 plus 6 plus 16 gives me 46 grams per mole. And when it asks for percent composition, that means of each individual atom. So if I want to find the mass of carbon, or the percent of carbon, I'm going to take carbon's individual portion of that, which is 24, divided by the whole. And I'm going to take that times 100. Okay, 24 divided by 46 times 100 gives me 52.2%. We do want at least a decimal here. We need to carry at least a decimal place to give us a little clearer picture. If I was looking at hydrogen, there are 6 hydrogens. So the percent of hydrogen would be 6 over 46 times 100. That gives me 13.0%. And then for oxygen, I would be at 16 divided by 46. And that gives me 34.8% oxygen. And we would label each of those as their percentage. What's a way I can check my percent composition work? To add them up to 100, right? They add up to 100. Okay, we're going to use an element or a compound's molar mass to help us convert between grams and moles, right? That is our conversion factor between grams and moles, is the molar mass. That's what we use to help us do that, okay? So all we're going to do is basically jump into some practice here, all right? How many moles are in 74.2 grams of, what's that compound's name? Magnesium chloride. Magnesium chloride, good. So how many moles are in 74.2 grams of magnesium chloride? What do I always start my T-chart with? What we know, yep. So I'm going to start my chart. I'm going to go from grams to mole. I can do that in one step, right? I can go grams to mole in one step. How did I know grams needed to go on the bottom? It's got to cancel. So here's grams. That means grams need to go on the bottom. Moles goes on the top. What does moles get here? The 1. And what has to go with grams? Molar mass. So let's calculate molar mass for MgCl2. We probably want to go ahead and carry that compound name all the way through the chart, especially as we get into stoichiometry. But for right now, it's not the end of the world. 74.2 divided by my molar mass gives me 0.779 moles. Does that answer seem rational for us? We know that a mole of it weighs 95.3 and we started with less than that. So it makes sense that our answer is coming out at less than 1 mole. Okay? Next one, how many grams are in 1.32 moles of MgNO3? 2 moles goes on the bottom, grams goes on the top. Moles gets a 1. Molar mass for magnesium nitrate, let's see here. That's what I had for my value of molar mass, 148.3. I don't know if you were somewhere in that ballpark or close to that. $195.8 grams. Okay, how do we feel about mole conversions? Is it coming all right back to us? Yeah. All right, good deal. When would we use Avogadro's number when we want to convert to what? Molecules or atoms. Good. Remind me of the difference between molecules and atoms. You know the difference? That's right. Molecules is what, like compound. Atoms would just be calcium by itself, potassium by itself, right? Anything by itself would just be considered an atom.
I have a sig fig question.
Yep.
So, are you going to be like picky about
Nope.
what sig figs?
Nope, really not. If I was doing this right, I should have rounded it to 196 grams, right? Because I started with 3 sig figs. Then my answer probably needs to finish in 3 sig figs. But no, I'm not going to be that picky about it. Here's what I'll say. I'll probably give you a sig fig either way. So if we're supposed to have 3, I'll count it right if there's 4 or if there's 2. You know what I'm saying? Yeah. You probably want to be more specific than less specific. But I'll try to give you a sig fig in either direction. Okay? But I just will be honest, it's not something that I look for a lot while I'm grading. Okay? If you round that to 200, that would be a problem, right? Because that's too much of a round. But for the most part, I think everyone here is fine with that. Okay, Avogadro's number, do we remember? Hopefully we knew what it was. 6.022 times 10 to the 23rd. Do we have it stored in our calculator still? Do you want it to be stored in your calculator? Or do we know how to do that? Okay. All right. If I have 1.42 moles of calcium nitrate, how many atoms are in that sample? This question, actually, I used the wrong version here. How many molecules are in that sample? Okay. Because I'm dealing with a compound, I should have used molecules instead of atoms, so I apologize. That was just a mistake on my part. Does it really matter to us here that we're talking about calcium nitrate? No, it makes no difference, right? Because if we're going from 1.42 moles and we're going from moles to molecules, I don't have to put in the molar mass anywhere. So it does not matter to us what actual compound we're using here, right? 1 mole, how many molecules are in 1 mole? It's 6.022 times 10 to the 23rd of anything. Do you remember how we abbreviated Avogadro's number? Na, right? That could be what you write there if you don't want to write out Avogadro's number every time. 1.42 times, I have it stored in my calculator as alpha N, and I got a value of 8.55 times 10 to the 23rd molecules. Okay, that's how many individual calcium nitrate molecules there are. CaNO3 2. Okay, now I want you to look at that chemical formula, CaNO3 2. There's 8.55 times 10 to the 23rd molecules of that substance right there. If I asked you how many molecules of calcium, just calcium, are in that sample, what would you tell me? It would be that number as well, because for every molecule of this, there is one single calcium atom. Okay, but if I asked you how many nitrogen atoms are in that sample, what would you tell me? It would be twice as much as that sample, because for every molecule of calcium nitrate, there are 2 nitrogen atoms. Does that kind of make sense? Do you see the ratio that's happening there? If I had, let's take it down to a smaller level. If I had 2 calcium nitrate molecules, CaNO3, 2, CaNO3, 2. If I had 2 of those and I asked you how many calcium atoms are there, well, there's 2. But if you had 2 of those molecules and I asked you how many nitrogen atoms are there, there'd be 2 and 2 more, which is 4. So there's twice as many, right? The mole ratio applies with that subscript as well. Okay, so I want you to be able to think through the ratios of individual atoms within that molecule. So if I would ask you, for example, how many oxygen atoms are found in that sample, you would take this number right here. Oops, I'm still on erase mode. You would take that number and you would multiply it by 6, right? Because there are 6 oxygen atoms per molecule. Okay, another way you could do it is you could keep working your chart to say molecules of CaNO3 2. One molecule is 6 oxygen atoms, and then you could go atoms from there, right? You're doing the same thing. You're going from molecules of the whole to atoms of the part, right, in that same scenario. But multiplying it right here in your chart is the same as multiplying it by 6 right there. Okay, so I want you to be able to see through the kind of difference there with looking at the ratio of individual atoms. Okay. If I have molecules of acetic acid, how many moles of acetic acid do I have? I'm going to start with what I know. I'm going to get rid of molecules. And I'm going to go to moles. This is Na. Remember, when we divide by Avogadro's number, we either use the stored number, we use the E function, or we have to use parentheses. But remember, I'm a big fan of using the E button. And so I got a value of 0.85 moles, 850 moles if I'm doing sig figs correctly. That would be acetic acid, C2H3OH. So, we're going to start with what we know, potassium hydroxide, 6.244 times 10 to the 23rd molecules. And what's potassium hydroxide's chemical formula? Yep, just KOH. KOH. All right, so we got to think about here, we're looking at specifically grams of oxygen, so it's going to add a step to our conversion here. We're going to go molecules of KOH to moles of KOH. Molecules is Avogadro's number. And moles gets the 1. And now we're going to keep going, right? Right now I'm in moles of KOH. So this is kind of an extra step in our T-chart here. We're going to go moles of our compound to moles of just oxygen. Okay? How many moles of oxygen are found in 1 mole of my compound? Or think about it on an atomic level. If I have 1 molecule of KOH, how many oxygen atoms do I have? Just 1. So this one happens to be a 1-to-1 ratio. Okay? But I have to put that step in there. So think of it almost as your mole ratio step right here. It really is your mole ratio step, but you're examining the ratio within a compound instead of between 2 different compounds, okay? So now I've gotten rid of moles of KOH, and I'm at moles of OH right now, but I want to get rid, moles of just O, and I want to go to grams of O. Yeah, great question. It does not have to be O2 here because it's still part of this compound. Still part of KOH. We're just seeing, it's almost like taking the percent composition of it. You could do it that way too. 16 grams. So now I can cancel moles of oxygen. I'm left with grams of oxygen. So I'm going to go ahead and take my math. And I get 16.6 grams of O. Okay, I want you to check yourself to see, does that seem reasonable? What did we start with here? Barely over a mole, right? Barely over a mole. And if we know 1 mole of KOH is 39 plus 16 plus 1, right? We have just over a mole of that substance. So it would make sense to us that our mass of oxygen is just over 16 grams, right? We've got just over a mole there. So we're looking at our mass being just over 16. Does this part of that make sense? The mole ratio step? Here it's within the compound, okay? So it's not just between 2 different compounds, which is kind of what we practiced a lot last year. This is actually now within a single compound, okay? Let's try this one as well. Okay, we'll kind of walk through this one together, and then we'll head out and do our homework here, okay? We're going to go lithium phosphate this time. 32.42 grams of lithium phosphate. Li3PO4 is, I think, the formula for lithium phosphate, okay? So we're going to go Li3PO4. Get rid of grams and go to moles of our compound. Let's see here. So I'm going to run lithium to 7. And I get a molar mass of 116. All right, then I'm going to get rid of moles of my compound, Li3PO4, and go to moles of just oxygen. So now I don't think my ratio is 1-to-1, right? In 1 mole of my compound, how many moles of oxygen atoms do I have? 4, right? That's where I get that number from. All right, then I'll finish from moles to molecules, or atoms, I guess I'll call it, since it's just oxygen. So atoms of oxygen. And I'll put in Avogadro's number there. So should we be expecting a really big number or a really small number? If I'm looking for atoms of oxygen. Really big, right? Times 10 to the 20 something. So 32.42 times 4 times Avogadro's number divided by 116 gives me a value of 6.73 times 10 to the 23rd. I guess I should go 732 times 10 to the 23rd atoms of oxygen. Now this one's a little tougher to see, is our answer reasonable? Does it make sense? Okay, the first thing that we're checking for is we're going for atoms. So we do have a large number of atoms, which is good. We started with, I don't know, roughly 1/4 of a mole, right? Somewhere around there. So it's kind of hard to see what's that going to be like, right? But you've got roughly 1/4 of a mole that you started with, but you've got 4 times as many oxygen atoms, so it comes out around a mole. I don't know. You can work your way through however you think is reasonable, but I think that answer seems good. Okay?